Conference will now be recorded.
Uh, Good afternoon, all. I think like most of you have joined, so I think we can start with the demo class. So good afternoon, all. I'm going to give a demo on DFT, which is Design for Testability. So before we go into what is called as DFT, we'll try to understand what is VLSI. So VLSI stands for Very Large Scale Integration. Very Large Scale Integration. Okay. So it means implementation of million transistors in a small area. So goals of VLSI, if a particular company is designing a chip, then there will be having some goals that has to be met. So that is what is a goal of VLSI. First one is high performance. So it actually it ensures faster processing. So ensuring faster processing. And then low power. So we are optimizing the power usage to extend the battery life. We are optimizing the power usage to extend the battery life. Okay, and then low area. So we are reducing the chip size in order to achieve compact products. We are reducing the chip size to achieve compact products. So this is how your chip will look like. Okay. So application stands for ASIC. Next we'll go to ASIC flow. So the full form of ASIC is application specific integrated circuit. Application specific integrated circuit, which means the IC which we are designing, it will be specific to a particular application. Okay. So for example, a modem chip can't be used as a chip which is used for deployment of airbag in your automobile. Can't be used as a chip which is responsible for deployment of airbag in your automobile, which is used for deployment of airbags in the automobile. Okay. So ASIC, the full form of ASIC is application specific integrated circuit. So which means the IC which we are designing, the integrated circuit, the IC which we are designing, it will be specific to a particular application. So say for example, a modem chip, it can't be used as a chip which is used for deployment of airbags in your automobile. Okay. And ASIC flow means it actually gives the steps which we need to follow for designing a chip. So ASIC flow means it actually involves the steps which is it is the steps which is involved in the process of chip design. Okay, so that is what is called as ASIC flow. Okay, so in the next slide we will try to see the various steps in the ASIC flow. Okay, so the first one is the design specification stage. So design specification stage means, so what will happen is based on the application for which we are designing the chip, certain specifications will be decided, like what has to be the speed, how many memory modules, processors, sensors are required, what has to be the power. So such kind of specifications will be decided. Okay, so based on the application, certain specifications like what has to be the speed, and then how many memory modules, okay, and then processors, sensors are required, what has to be the power. So such kind of specifications will be decided. Okay, and after that we have the design code stage. So like the design So the design team will be writing the design code of the chip. So they will be describing the functionality of the chip. Okay, so the design team will write the design code of the chip. Will write the design code of the chip. Design code of the chip. So they basically describe the functionality of the chip. They describe the functionality of the chip. Okay, so this design code, it will be in behavioral model or data flow level model. So this will be in behavioral model or data flow level model. Okay, and then we have the verification team. So verification team, they validate the functionality of a design to ensure that it meets the required specification and performs as intended. Okay, so verification team, they will validate the functionality of a design to ensure that it meets the required specification, to ensure that it meets the required specification and performs as intended. Okay, so validate the functionality of a design to ensure that it meets the required specifications and performs as intended. So that is what will be done by the verification team. And afterwards, we have the synthesis team. So synthesis, what do they do? The behavioral and data flow level model code, it will be converted to structural form. So behavioral or data flow level model code. So it will be converted into structural form. It will be converted to structural form, or we can say that it will be converted to a technology node specific gate level netlist. Technology node specific gate level netlist. Okay. And then after the synthesis team, we have the DFT team. We will understand about DFT team in the upcoming slides. Okay, in the upcoming slides, we'll try to understand more in detail about the DFT team. Okay, what is DFT team? We'll try to understand it more in detail in the upcoming slides. Okay. And then we have the physical design team. So physical design team, they actually convert the gate level design into layout form. So physical design team, they convert the gate level design to layout form. Gate level design into layout form. Okay. And then we have the sign off. So in sign off, we have the STA and then physical verification PV and then logical equivalence check LEC. Okay. So STA, the full form of STA is static timing analysis. So as its name suggests, it is a method of validating the timing performance of a design by checking all possible paths for timing violations. So that is what is STA. And then we have the physical verification PV. So it is actually to verify the layout of the circuits. And then we have logical equivalence check LEC. Okay. So LEC, it is actually done to check whether the final design is logically equivalent to the original design or not. So the reason is because if you see in the process of chip design, our design is undergoing a lot of stages. So if you see, first we had the behavioral or data flow level model code, and then it got converted into structural form. Okay, and if you're going for low power design, certain special cells have to be added, like level shifters, clock gating, isolation cells, retention registers, like that certain special cells will be added. And DFT team, we will be adding our own test structures like scan insertion, embed insertion, boundary scan insertion, like that we will be adding our own test structures into the design. Okay, so if you see in the process of chip design, in each and every stage, our design is undergoing a lot of changes. So that is why LEC is done to check whether the final design is logically equivalent to the original design or not. Okay, so like actually LEC will be done after each stage. So like after synthesis, after DFT, after PD, like that LEC will be done after each stage. Okay. And afterwards, we have the tape out. So tape out means it is actually delivering the database to the manufacturing unit. So delivering the database to the manufacturing unit is tape out. So delivering the database to the manufacturing unit. So that is what is called as tape-out, delivering the database to the manufacturing unit. And finally, we have the packaging and testing. So packaging and testing, it is actually done after manufacturing. Packaging and testing is done after manufacturing. So packaging means, so here if you see, this complete circle is the wafer, and this small portion in it is called as the die. So covering this die with a protective layer is called as packaging. And testing means it is actually done to check whether our chip is good or not, whether there are any manufacturing defects or not. So that is what is called as testing. Okay. So now in our upcoming slides, we will try to focus more in detail about this verification team, design for testing, and then regarding this testing. Okay, so we will try to focus more in detail about all these things. Okay. So what is DFT? So DFT means, DFT is to insert test structures into the design. So we will be adding our own test structures into the design, like scan insertion, embed insertion, boundary scan insertion. Like that, we will be adding our own test structures in the design. So during the pre-silicon stage means before manufacturing. Pre-silicon stage means before manufacturing. To facilitate means to help detection of manufacturing defects in the chip. Okay. So, which means if a particular chip, so if suppose a particular chip fails after manufacturing, DFT engineers will be able to tell what manufacturing defect has caused the chip to fail. Okay. So, DFT engineers will be able to tell what manufacturing defect has caused the chip to fail. What manufacturing defect has caused the chip to fail. Okay. So DFT is to insert test structures in the design during the pre-silicon stage to facilitate, that is to help the detection of manufacturing defects in the chip. So if suppose a particular chip fails after manufacturing, DFT engineers will be able to tell what manufacturing defect has caused the chip to fail. Okay. And what is the role of DFT engineers? So as we discussed in the previous slide, DFT is to insert test structures in the design during the pre-silicon stage to facilitate the detection of manufacturing defects in the chip. Okay. So DFT engineers, we do not check the functionality of the chip. We rather check the quality of the chip. Okay. So DFT engineers do not check the functionality of the chip. We rather check the quality of the chip. So we'll try to understand the difference between DFT engineer and then a functional verification engineer. So in the ASIC slide, we had seen a functional verification engineer as well, right? So we'll try to understand what is the difference between the role of a DFT engineer and the role of a functional verification engineer. Okay. So why do we need a DFT team when we have functional verification team? Okay. Why do we need a DFT team when we have a functional verification team? Okay. So let's try to understand here. So consider that you are having a design. Okay. So your design is a 10-bit counter with a counter initialization and a counter observation circuit. So say that the counter is manufactured with a defect. So after counting 999, instead of counting 1000, it is once again counting 999. Okay. So we'll try to understand what will happen if only functional verification team is there and what will happen if a DFT team is there. Okay, we'll try to understand both the cases. So now the first case we will consider what will happen if only functional verification team is there. Okay, we'll try to understand what will happen if only functional verification team is there. So in our case, what is happening? So the counter is manufactured with a defect. So that is why after counting 999, instead of counting 1000, it incorrectly rolls back to 999. Okay, so counter is manufactured with a defect. So that's why after counting 999, instead of counting 1000, it incorrectly rolls back to 999. Okay, so now if only functional verification team exists, then what will happen? Functional team, they will test the counter using functional patterns. So in this case, it will take more than 1000 clock pulses to tell that the counter is failing. It will take more than 1000 clock pulses to tell that the counter is failing. So why is it like that? Okay, the why is it like that is, okay, because functional verification team, they will check the functionality. Functional verification team, they will check the functionality. Check the functionality. Okay, so which means they will check if the counter properly counts from 0 to 1023. Okay, so that is, they will check if the counter counts from 0 to 1023. Counts from 0 to 1023. Okay. So in this case, our counter, it is failing at the 1000th pulse. Okay. Because at the 1000th pulse only, counter is again counting 999 instead of 1000. Okay. So in our case, counter is failing at the 1000th pulse. The counter is failing at the 1000th pulse. Okay. So that is at the 1000th pulse, counter is again counting 999 instead of 1000. Okay, at the 1000th pulse only, counter is once again counting 999 instead of 1000. Okay, so that is at the 1000th pulse. Okay, counter is again counting 999 instead of 1000. Counter is again counting 999 instead of 1000. Okay, so for this itself, 1000 pulses are required. So for this itself, 1000 pulses is required. Okay, 1000 pulses are required. Okay. And some more clock pulses will be required for counter initialization and counter observation. Counter initialization means the counter, it has to be brought to the initial state, and counter observation means the output of the counter, it has to be taken to some register and the register has to be read. Okay, so that's why some more clock pulses are required for counter initialization and counter observation. Some more clock pulses are required for counter initialization and counter observation. Counter initialization and counter observation. Okay, so that is why functional verification team, it will take more than 1000 clock pulses to tell that the counter is failing in this case. Okay, so you can just read this slide once. I'll give you 2 minutes time. You can just read this and try to understand. Sudhakar, counter means it is a circuit which counts. So like, a binary counter, right? 2-bit binary counter means it will be like 0001111. Afterwards, again, it will count from 0001111. So like that, it's a counter. It actually counts. Okay, up counter, down counter, those things which will come in the which you would have learned it in the digital design class, right? In your college, in your digital design class, you would have learned about the counters. So that is what is a counter, which actually counts the which actually counts. Okay. So you can just read this and you can try to understand. I'll give you 2 minutes time. Okay. And next is another thing is So functional team, they can only tell that the counter is failed. Functional team, they can only tell that the counter is failed. So why? So like because functional team, they will check the functionality. Functional team, they will check the functionality.
It checks only the functionality of the counter.
Yes, yes, correct. So functional team, they will check the functionality. Okay. So which means they will check if the counter counts from 0 to 1023 properly or not. Yes, as Sudhakar has said correctly, they will check if the counter counts from 0 to 1023 properly or not. So check the functionality means that is they will check if the counter counts from 0 to 1023. Counts from 0 to 1023 properly or not. Okay. So in this case, what is happening? Counter, after counting 999, instead of incrementing to 1000, it is once again counting 999. Okay. So in this case, after counting 999, okay, instead of incrementing to 1000, okay, it is once again counting 999. It is once again counting 999. So counter is failing. Counter is failing. Okay, so functional team, they can only tell that the counter is failing. The reason is because they will check the functionality, that is, they will check if the counter counts from 0 to 1023 properly or not. So in this case, after counting 999, instead of incrementing to 1000, it is once again counting 999. So counter is failing. Okay. Now, we will try to understand what will happen if a DFT team is existing. So what is our scenario? Our scenario is our counter is manufactured with a defect. So after counting 999, instead of counting 1000, it once again counts 999. It incorrectly rolls back to 999. Okay. So now, what will happen if a DFT team exists? So if DFT team exists, DFT patterns are used to test the chip. So in this case, DFT team will be able to tell that the counter is failing approximately in the range of 100 clock pulses. Range of 100 clock pulses means you can imagine like 80, 90, 100, 120, like that. In the range of 100 clock pulses.
Is my voice audible? Like I got a prompt that my voice got disconnected. Is my voice audible? Okay. Uh, Messi is every counter will count up to 1023. So the answer to your question is like a 10-bit counter will count from 0 to 1023. If you consider a 2-bit counter, it will count from 0 to 3. So 0, 1, 2, 3. Okay, 2-bit counter 0, 0, 0, 1, 1, 0, 1, 1. Okay, like that. So the counter. So if you consider a 2-bit counter. So 2-bit counter means it will count from 0 to 3. So 0, 0, 0, 1, 1, 0, 1. And then once again it goes back to 0, 0. Same sequence will repeat. Same thing if it is 3-bit counter means it will count from 0, 0, 0, 0, 0, 1. It counts till 1, 1, 1 and then it once again comes back. Same way 10-bit count means 0 to 1023 it will count. It depends on the number of bits of the count. Sudhakar, demo session notes will not be shared. When you enter into the regular course, so those notes will be shared. Okay, so the demo session notes will not be shared, but we'll be covering all these slides once again in the regular course as well. So once you come into the regular course, those slides will be shared. Okay. So, So let's come back here. So DFT, we will be able to tell that the counter is failing approximately in the range of 100 clock pulses. Range of 100 clock pulses means somewhere around 80, 90, 100, 120, like that, in the range of 100 clock pulses. So if you see, we actually require less number of clock pulses compared to functional verification team. So functional verification team, as we discussed in the previous slide, they require more than 1000 clock pulses. More than 1000 clock pulses. Whereas DFT team, DFT team, DFT team, we require somewhere around 80 or 90 or 120, like that. In the range of 100 clock pulses we require. So if you see DFT team, we require less number of clock pulses compared to functional verification team. So that is why test time will be less compared to functional verification team. Okay, so that's why test time will be less compared to functional verification team. And how DFT team we are able to tell that the counter is failing in such less number of clock cycles? It is because we go for a technique called as scan insertions. We go for a technique called as scan insertions. Because of that, we will be easily able to control and observe our circuits. Okay, we will be going for a technique called as scan insertions. Because of that, we will be easily able to control and observe our circuits. Okay. Next, DFT team, we will be able to tell that the counter is failing, and we will also tell what manufacturing defect has caused the counter to fail. Okay, DFT team will be able to tell that the counter is failing and also tell what manufacturing defect has caused the counter to fail. So how DFT team is able to give this detail? It is because DFT patterns are generated using a technique called as ATPG. So ATPG tool, it actually does fault simulation to generate the test pattern. It actually does fault simulation to generate the test pattern. Okay, so that is why DFT team, we will be able to tell what manufacturing defect has caused the counter to fail. Okay, in our course you will be understanding like what is scan insertion, what is ATPG, what is fault simulation. All those things we will be understanding it when we do our regular DFT advanced course. When we do, you will be able to understand. Okay, so yeah. So now the conclusion is, so we can conclude it here. So here in this case, with DFT patterns, if you see, okay, with DFT patterns, test time will be less compared to functional patterns. As we discussed in the previous slide, with DFT patterns, test time will be less compared to functional patterns. And with DFT patterns, we will be able to tell what manufacturing defect has caused the chip to fail. So if you see DFT patterns, it has these advantages over functional patterns. So that's why DFT patterns will be used to test the chip after manufacturing. Some functional patterns will also be used to test the chip after manufacturing, but majority DFT patterns will be used to test the chip after manufacturing. Okay, so with DFT patterns, test time is less compared to functional patterns, and with DFT, we will be able to tell what manufacturing defect has caused the chip to fail, as we discussed in the previous two slides. Sorry. So as DFT patterns has these advantages over functional patterns, DFT patterns will be used to test the chip after manufacturing. So some functional patterns will also be used to test the chip after manufacturing, but majority DFT patterns only will be used to test the chip after manufacturing. Okay. So now we are trying to understand the role of a DFT engineer. Now can you tell, like if DFT patterns are used to test the chip after manufacturing, why do we need a functional verification? Can anyone guess?
Madam, functional verification team will give the values and they will check the output only. And after manufacturing, we may occur the nodes have problem. We are identifying the nodes, madam, where the node is fault by giving these values, DFT patterns.
Ma'am, functional team will check the functionality functionality of the chip, whether it is functioning properly or not.
Yes, correct. Both your answers are correct. Okay. So if DFT patterns are used to test the chip after manufacturing, why do we need a functional verification team? Let's try to understand with the help of an example. So this is a half adder. So for half adder, sum is equal to A plus B, carry is equal to AB. Whether this is correct? No. Here we are having a functional bug. So sum should have been A XORed with B, carry is AB. But mistakenly someone has written sum is equal to A plus B, carry is equal to AB. This is a functional bug. Now for time being, consider that you don't have a functional verification team. Okay, for time being, consider that you don't have a functional verification team. Directly the design has got synthesized. So if you see, a wrong design has got synthesized. And this design is given to the DFT team. So DFT team, we will generate pattern just to check whether there are any manufacturing defects in each and every net of this design or not. Okay, DFT team, we will generate patterns just to check whether there are any manufacturing defects in each and every net of this design or not. Okay, and then what will happen? Chip has got manufactured and DFT patterns are applied onto the chip. So input sequence is applied onto the chip. Output of the chip, it is compared with the expected output. Sorry. So output of the chip, it is equal to the expected output, which means there are no manufacturing defects. But whether the design will function like a half adder in this case, whether the design will function like a half adder in this case. So output of the chip, it is equal to the expected output. It means that there are no manufacturing defects. But whether the design will function like a half adder? No, because even though there are no manufacturing defects, the circuit will not function like a half adder. Why? The design itself is wrong. So here if you see at the design stage, the design itself is wrong. The design itself is wrong. Wrong design has got synthesized. It was given to the DFT team. So DFT team, we generated patterns just to check whether there are any manufacturing defect in each and every net of this design or not. Then the chip got manufactured. DFT patterns are applied. Output of the chip is compared with the expected output. Both are equal. So there are no manufacturing defects. But even though there are no manufacturing defects, this circuit will not function like a half adder. Why? The design itself is wrong. So that is what is the significance of the functional verification team. They will be validating the functionality, whatever is there here, whether this is correct or not, whatever is written, whether that is correct or not. So that is what will be validated by the functional verification team. They will be validating the functionality. Okay. So now we will try to understand about the testing. So in the ASIC flow slide, we had a slide called as testing, right? So at that time, I had told that this is actually done after manufacturing. So this testing is actually done after manufacturing. So testing, it is a process of determining whether a device is good or not. Okay. So which means whether our chip is good or not, whether there are any manufacturing defects in our chip or not. Okay. So testing includes test pattern generation, application, and output evaluation. So basically these test patterns are there, right? So as I discussed in the previous slide, these test patterns, it will be generated by the DFT engineer before manufacturing. So it will be generating the test pattern. So it will be consisting of the input sequence and expected output. So what will happen? This input sequence will be applied onto the chip, and then the output of the chip will be compared with the expected output. So output of the chip, if it is equal to the expected output, means chip is good. So there are no manufacturing defects. Output of the chip, if it is not equal to expected output, means it means that the chip has failed. So there are some manufacturing defects in the chip. If a particular chip fails, DFT engineers will be able to tell what manufacturing defect has caused the chip to fail. Okay, if a particular chip fails, DFT engineers will be able to tell what manufacturing defect has caused the chip to fail. Okay. And basically, there are four possible outcomes of this testing. So if a good IC, if it passes the test, it is called as true pass. And a defective IC, if it fails the test. So a defective IC, if it fails the test, it is called as true reject. Okay. Now, if a defective IC, if it passes the test, if it passes the test, it is called as test escape. It is also called as under testing. And if a good IC, if it fails the test, it is called as yield loss. It is also called as over testing. Okay. So goal of good testing, it is actually to reduce the test escape and yield loss. Okay. Goal of good testing is to reduce the test escape and yield loss. So yield means number of good chips divided by the total number of chips. Okay, yield means number of good chips divided by the total number of chips. Okay. So now we'll try to understand what is called as manufacturing defects. Okay, what is called as manufacturing defects? So the defects that are caused by process variation and random imperfections. So that is what is called as manufacturing defects. So process variation means slight variation in transistor channel length, metal interconnect width and thickness. So all those things will impact the logical and timing performance. Okay, and then random imperfection. Random imperfection means it can result in unintentional shorts, unintentional opens. So that is what is called as random imperfections. Okay. So that is what is manufacturing defects. So manufacturing defects are nothing but the defects that are caused due to process that are caused by process variations or random imperfections. Okay. So now we will try to understand the flow of DFT. So this is the flow of DFT. So first is insertion. So we will be like inserting our own test structures into the design, like scan insertion, embedded insertion, boundary scan insertion, like that we will be adding our own test structures into the design. And then we have the generation. Generation means we'll be generating the test patterns. And finally, we will be going for the validation. So that is done using simulations. We'll try to understand about each of these stages in the upcoming slides. Okay, in the upcoming slides, we will try to see a course overview. Okay, we will try to see our course overview, and simultaneously, we will also try to cover the flow of DFT. Okay, so basically, this is our course outline. So in our course outline, so first we'll be covering the scan insertion, and then we will be covering the scan compression. So scan compression, it is also called as EDT insertion. Scan compression, it is also called as EDT insertion. And then we will be having the OCC, which is on chip clock controller. And then we'll be having ATPG, which is automatic test pattern generation. And then we will be having simulations. So in our simulations in our course as of now, only no timing simulation is covered. Only no timing is covered in our course as of now. Okay. And then JTAG. JTAG means Joint Test Action Group. So it is actually a IEEE 1149.1 standard. Okay. We will also be covering IJTAG. So which is nothing but IEEE 1687 standard. Okay. And then MBIST, Memory Built-in Self-Test and Boundary Scan. Okay. So now we will try to understand in short about what are the things we are going to focus in each of these topics. I'll just try to give you an overview about it. Okay. So first coming to the scan insertion. So scan insertion, what will happen during scan insertion is, so all the normal flops in the design, they will be converted to scan flops, and these scan flops, they will be stitched into scan chains. So that is what is scan insertion. So all the normal flops, they will be converted to scan flops, and these scan flops, they will be stitched into scan chains. So that is what is called as scan insertions. Okay. So now we will try to understand what is the need of scan insertion. So why do we need to convert all the normal flop to scan flops, and then why do we need to stitch the scan flops into a scan chain? So why do we need to do all those things? We'll try to understand. Okay. So need of scan insertion, it is actually to gain controllability and observability of the design. Okay, need of scan insertion, it is actually to gain controllability and observability of the design. So in order to easily control and observe our design, we will be going for scan insertion. And when we do this course in detail, when you do the DFT advanced course, you will be able to understand clearly the need of scan insertion. Okay, we are saying that in order to easily control and observe our circuit, we'll be going for scan insertion. So when we do our course with the help of various illustrations, we will explain the need of scan insertion. But as of now, I will just give a quick idea on it. Okay, I'll just give a quick idea on it. Okay, what is the need of scan insertion? I'll just give a quick idea. So in the course, when you do the course, you will be able to understand what is the need of scan insertions. Okay, why do we need to go for scan insertions? Okay. So there is some echo in my voice. Okay, let me just check. Is the problem same for everyone? Is my voice echoing? Okay, let me just check.
How about now? Is it clear or is it still echoing? Okay. So we go for scan insertion in order to easily control and observe our circuit. So you will be able to understand it in detail when we do the course. Okay, when we do the course, you will be able to understand it in detail. How with the help of scan insertion, you are able to easily control and observe our circuit. You will be able to understand it in detail when you do the advanced course. Okay, regular course when you do. So as of now, I will just try to give you an idea on why we go for scan insertions. Okay. So here in our case, the same counter example, so which we discussed. So we were having a 10-bit counter with a counter initialization and a counter observation circuit. So the counter is failing. That is after counting 999, instead of counting 1000, it again counts 999. Okay, after counting 999, instead of counting 1000, it again counts 999. Okay, so how many clock pulses are required by functional verification team and DFT team to find out that the counter is failing? So as I explained in the previous slides, while discussing about the difference between DFT and functional verification engineer, I already explained that functional verification team, they require more than 1000 clock pulses to detect that the counter is failing in that case. Okay, so we have already seen that functional verification team, they require more than 1000 clock pulses to detect that the counter is failing in that case. So how? Already in the previous topic, I had explained it. Now, DFT team, we will be able to tell that the counter is failing approximately in the range of 100 clock pulses. Range of 100 clock pulses means, so as I told, so somewhere around 80, 90 or 120 like that. Okay, so if you see DFT team, we require significantly less number of clock cycles compared to the functional verification team. Okay, DFT team, we require significantly less number of clock cycles. Less number of clock cycles compared to the functional verification team. Compared to the functional verification team. Okay, DFT team, we require significantly less number of clock cycles compared to the functional verification team. Okay, so how DFT team are able to tell that the counter is failing in such less number of clock cycles? How DFT team is able to tell that the counter is failing in such less number of clock cycles? It is because we go for scan insertions. We go for scan insertions. Because of that, we are easily able to control and observe our circuit. Okay, and how it is like that, with the help of various illustrations, we will explain it, we will show you during the regular course. So as of now, just try to see that we are going for scan insertion technique. So because of that, we are able to easily control and observe our circuit. So that's why in this particular case, DFT team, we require significantly less number of clock cycles compared to the functional verification team to tell that the counter is failing. Okay, so just get an idea as of now. When we do the course, you will be able to get more clarity on it. Okay, and now we will try to understand what are all the topics will be covered here in the scan insertion. Okay, so in the scan insertion topic, what are all the things we will be covering it, we'll try to understand. So our first topic, topic 1 is scan insertion. Okay, so in scan insertion, so we will be like understanding about the scan cell functionality. We will understand about the scan cell functionality. We have seen that all the normal flops will be converted to scan flops. Okay, so we'll understand the functionality of the scan cell, and then we'll try to understand the functionality of scan chain. Okay, so all the scan flops, they will be stitched into a scan chain, right? So functionality of scan chain, we will try to understand. And then we will try to understand the need of scan insertion. whatever, like we'll be easily able to control and observe our circuit, right? So we'll try to understand how, if you go for scan insertion, you're able to easily control and observe our circuit. We'll try to understand that how. Okay, in order to understand this, you first need to understand the functionality of scan cell and scan chain. Okay, so that's why as of now, I just given an idea. When we do the course, we will cover it in detail about the need of scan insertion. Okay, and then basically, what is scan insertion? So scan insertion means all the normal flops, they will be converted to scan flops. So that is what is called as scan insertion. All the normal flops, they will be converted to scan flops. So if a normal flop, if it has to be converted to scan flop, then it has to pass certain rules. It has to pass certain rules. Okay, if a normal flop, if it has to be converted to scan flop, then it has to pass certain rules. So those rules are only called as the scan DRCs. Those rules are only called as the scan DRCs. Okay, what is DRC? DRC means design rule check. Design rule check. Okay, so if a normal flop, if it has to be converted to scan flop, then it has to pass certain rules. So those rules are only called as the scan DRCs. DRCs means design rule check. Okay, so there will be various scan DRCs, like we'll be understanding about the clock controllability DRC. Okay, we'll be understanding about the clock controllability DRC. Various DRCs we'll understand. Okay, set reset controllability DRC. Okay, and then we'll understand about the potential raise DRC. We'll understand about the feedback loop DRC. We'll understand about the X source DRC. We'll understand about the bus contention DRC. All those things, these are the various DRCs. We'll understand about all these DRCs in our scan DRCs topic. Okay, and then we will try to understand about what is called as scan chain balancing. Okay, what is called as scan chain balancing. Okay, so what is scan chain balancing? Scan chain balancing means keeping almost equal number of flops in the scan chains is called as scan chain balancing. Okay, keeping almost equal number of flops in the scan chains is called as scan chain balancing. Keeping almost equal number of flops. Almost equal number of flops in the scan chain. So that is what is called as scan chain balancing. Keeping almost equal number of flops in the scan chain is called as scan chain balancing. Okay. So say for example, in scan chain 1, you are having 1000 flops. In scan chain 2, you are having 1000 flops. In scan chain 3, you are having 999 flops. So this is called as balanced scan chains. This is what is called as balanced scan chains. Okay, so scan chain balancing means keeping almost equal number of flops in the scan chain. So in scan chain 1, you're having 1000 flops, scan chain 2, you're having 1000 flops, scan chain 3, you're having 999 flops, means these are called as balanced scan chains. Okay, so why do we need to go for scan chain balancing? Why do we need to go for scan chain balancing? We go for scan chain balancing in order to reduce the test time. Reduce the test time. How is it? We will discuss in course. We will discuss in course. Okay. How if you go for scan chain balancing, you are able to reduce the test time. We will discuss it in course. Okay. Why are we going for scan chain balancing? In order to reduce the test time. And how if you go for scan chain balancing, you are able to achieve reduction in test time? We will discuss it with the help of various illustrations in our course. Okay. And if you want to go for scan chain balancing, that is in order to achieve scan chain balancing, you need to adopt certain techniques called as edge mixing and domain mixing. Okay, in order to achieve balancing, in order to achieve balancing, we need to adopt edge mixing and domain mixing. We need to adopt edge mixing and domain mixing. Okay, so in order to achieve balancing, we need to adopt edge mixing and domain mixing. Okay, so what is this edge mixing? What is this domain mixing? And how, if you go for edge mixing and domain mixing, you're able to achieve balancing? All these points we will discuss it when we do the course. Okay, now if you go for edge mixing and domain mixing, again it will introduce some problem. What problem it will introduce? That is what we will discuss next. Problems in edge mixing and domain mixing. Problems in edge mixing and domain mixing. Problems in edge mixing and domain mixing, and then its solutions. How to overcome the problem? What is the solution? We will try to understand. Okay, what are the problems in edge mixing and domain mixing and their solutions? We will try to understand. Okay, so these are the major topics which we'll be covering it as a part of our scan insertion class. Apart from that, we'll also be covering some more small topics like definition type topic, like types of scan cells, benefits of scan, and then like some more, like some definition kind of topics we'll be covering it. Short topics we'll be covering it during the course. But these are the major topics which will be covered during our scan insertion class. Okay. And then the next topic is scan compression. What is scan compression? Scan compression means a single scan channel is internally divided into multiple chains. Or else you can say that internal scan chains are compressed into external channels. Okay, internal scan chains are compressed into external channels. Okay, internal scan chains are compressed into external channels. So like this, you have your internal scan chains like this. These are your internal scan chains. So these internal scan chains, they are compressed into external channels. Like this. They will be compressed into external channels. This is your external channel input, and this is your external channel output. So that is what is called as scan compression. So you have your scan chains. So normal flops will be converted to scan flops. They will be stitched into scan chains. So those scan chains will be calling it as the internal scan chains. They are compressed into external channels. And why? Why do we need to do this? Why do we need to compress the internal scan chains to external channels? Why do we need to go for scan compression? We need to go for scan compression in order to reduce the test time and in order to reduce the test data volume. So in order to reduce the test time and in order to reduce the test data volume, we will be going for scan compression. And how? How, if you go for scan compression, you are able to achieve reduction in test time, you are able to achieve reduction in test data volume. Test data volume means it is the number of bits of patterns. Test data volume means it is the number of bits of patterns. Okay, so how if you go for scan compression, you are able to achieve reduction in test time, you are able to achieve reduction in test data volume. We will understand it logically. Okay, and we will also understand with the help of formula. We will also understand this with the help of formula when we do the course. We will understand it logically and we'll try to understand it with the help of formula when we do the course. Okay. So now basically in order to achieve scan compression, if you are using mental graphics tools, okay, to achieve scan compression. So if you are while using mental graphics tools, okay, okay, we will be adding up a logic. What is the logic? It is the EDT logic. We'll be adding up a logic. So that is nothing but the EDT logic. The full form of EDT is embedded deterministic test. Embedded deterministic test. Deterministic test. Okay. So in order to achieve scan compression, if you are using mental graphics tools, you'll be adding up a logic. So that logic is called as the EDT logic. So the full form of EDT is embedded deterministic test. Okay. So here, if you see here, these are the internal chains, and these are nothing but your external channels. These are your external channels. In between, if you see, you're able to see certain components called as decompressor, compressor, like that. You're able to see certain components. Okay, you're able to see some components called as decompressor, compressor, like that. You're able to see some components. So these components are a part of the EDT logic. This decompressor, compressor, these components are actually a part of the EDT logic. Okay, so these are all part of EDT logic. Okay, so in order to achieve scan compression, if you're using mental graphics tools, you'll be adding up a logic called as EDT. Full form of EDT is embedded deterministic test. So if you see you're having internal chains and external channel, in between the internal chains and external channel, if you see you're able to see certain components called as decompressor and compressor. You're able to see certain components called as decompressor and compressor. So these components are a part of the EDT logic. Okay, so basically in EDT logic, these are the 4 components. EDT logic, it will be having 4 components. Okay, you'll be having 4 components. So what is it? You will be having the decompressor. You'll be having the decompressor. Okay, and then you are having the compressor or compactor logic. You are having the compressor or compactor logic. Okay, and then you are having the controller logic. And you will be having the bypass logic. So I have not represented everything here. I've just shown only the decompressor and compressor components alone. When we do the course, I will show you the EDT structure with all these components present. As of now, I have not shown all the components. I've just shown only the decompressor and compressor. Okay, when we do the course, we will try to understand the complete EDT logic structure. Okay, so these are the 4 components in EDT. One is the decompressor, other one is the compressor or compactor logic. Then you have the controller logic, and then you'll be having the bypass logic. Okay. So in scan compression, what are all the topics we will be covering? It is. So in scan compression, what are all the topics we'll be covering is. Okay. So first we will try to once again understand what is scan compression. As of now, I've just given an overview. When we do the course, we will try to understand more in detail about what is scan compression. And then we will try to understand the need of scan compression. Need of scan compression. What is the need of scan compression? One is reduction in test time and the other one is reduction in test data volume. So reduction in test time, and reduction in test data volume. Reduction in test data volume. Okay, need of scan compression is reduction in test time and reduction in test data volume. So this is what? How? When we do this topic, we will understand both logically as well as with the help of formula. We will take the formula for test time, we'll take the formula for test data volume. We will substitute both the things. Okay, we'll substitute the values and we will try to see with the compression and without compression, we will try to compare the values and we will try to understand if you go for scan compression, how you are able to achieve reduction in test time and reduction in test data volume. Okay, and we will also explain logically without using formula. Logically also we will explain that. Okay, and then there is a there will be a quantity called as compression ratio. Okay, there will be a quantity called as compression ratio. Okay, there will be a quantity called as compression ratio. So compression ratio formula is number of internal chains by number of external channels. Number of internal chains divided by number of external channels. Number of external channels. So that is what is compression ratio. Okay, compression ratio means number of internal chains divided by number of external channels. So this compression ratio quantity, we will make sure that it doesn't exceed above 100x. This compression ratio, we will make sure that it doesn't exceed 100x. It doesn't exceed 100x. Okay, this compression ratio, we will make sure that it doesn't exceed 100x. So why? Why is it like that? We'll try to understand. Okay, when we do the course, we'll try to understand the reason. Okay, so compression ratio quantity, we will make sure that it doesn't exceed 100x. So why is it like that? Why? What problems it will cause if it is exceeded above 100x? We'll try to understand it when we do the course. Okay, we make sure that it doesn't exceed 100x. So why? We'll try to understand it. And we will also try to understand about the merits and demerits of this high and low compression ratio. We'll try to understand about the merits and demerits of high and low compression ratio. High and low compression ratio. Okay, we'll try to understand the merits and demerits of high and low compression ratio. Okay, and then we will also try to understand how to decide the number of internal chains and external channels. Okay, so how to decide that we will try to understand. Okay, so for a particular design or for a particular project, how to decide the number of internal chains and external channels. So this is your internal chain. These are your internal chains, and these are nothing but your external channels. So if you're considering, if you're doing a particular project for a particular design, how will you decide the number of internal chains and external channels? So that also we will cover. Okay, so how deciding the number of internal chains and external channels. Deciding the number of internal chains and external channels. Internal chains and external channels. Okay, and then we will try to understand about the EDT logic. We'll try to understand about the EDT logic. So as I told, if you're going for scan compression, if you're using Mentor graphics tool, then you need to add up a logic. So what is the logic? EDT logic. Okay, so as you know, inside EDT logic, you'll be having these components. So you'll be having a decompressor component, and then you'll be having a compressor component, compressor, or you can even call it as a compactor, compressor or compactor, compressor or compactor component. And you will be having a controller component. You will be having a controller component. Okay, so you'll be having the mask inside the controller. You will be having the mask shift register, and then you'll be having the mask hold register. Okay, and you'll be having decoders. Again, decoders, there will be two things. One will be the one hot decoder, other one will be the XOR decoder, all those things. Okay, and then you'll be having the bypass logic. You'll be having the bypass logic. Okay, so these are all the components of the EDT logic. So you'll be having a decompressor, then you'll be having a compressor or compactor logic. You'll be having a controller logic. Inside controller, you have this mask shift register, mask hold register, and then the decoders. So one hot and XOR decoder. And then you'll be having the bypass logic. So we will try to understand about each and everything. So decompressor means what is the structure of decompressor? What role it plays in scan compression? Okay, same way compressor means what is the structure of compressor? What role it plays in compression? Okay, same way controller and bypass logic, each and everything will try to understand its functionality in detail when we do the EDT logic. Okay, and then we will also be understanding about some topics like pipeline flops in compressor. Okay, why pipeline flops are added in compressor. Okay, And then we will also understand about the lockup cells in EDT, lockup cells in EDT. So all those things we will try to understand. Okay. So these are all the topics. We will be covering it as a part of our scan compression topic. Okay. And next one is ATPG. So full form of ATPG is automatic test pattern generation. Okay. Full form of ATPG is automatic test pattern generation. Okay. So it is a process of generating test patterns for a given fault model like StuckCAD, TDF, PDF, IDDQ. There will be various fault models. So it is a process of generating test patterns for a given fault model. Okay. So during ATPG, test patterns will be generated. These test patterns will be used to test the chip after manufacturing, as we already discussed in our earlier slides. So these test patterns should be having a capability. So what is the capability? After manufacturing, if suppose there are any defects, these test patterns should have the capability to detect most of the manufacturing defects. Okay. And how are we sure that our test patterns will be able to detect most of the manufacturing defects? It is because our tool does a process called as fault simulation in order to generate the test patterns. Okay. So ATPG, full form of ATPG is automatic test pattern generation. So as its name suggests, it is a process of generating test patterns for a given fault model like StuckCAD, TDF, PDF, IDDQ, like that. So during ATPG, test patterns will be generated. These test patterns will be used to test the chip after manufacturing. And these test patterns should be having a capability. So after manufacturing, if suppose there are any defects, these test patterns should have the capability to detect most of the manufacturing defects. So how are we sure that our test patterns will be able to detect most of the manufacturing defects? So it is because our tool does fault simulation in order to generate the test patterns. Okay. So this ATPG, it is not a very straightforward topic. It is a very vast topic and it is also not a very straightforward topic. So it will take minimum 10 to 12 sessions to complete it. Okay, minimum 10 to 12 sessions it will take to complete this ATPG topic. So it's not a straightforward topic and it is a very vast topic. So it will take at least 10, minimum 10, maximum 12 sessions to complete this topic. Okay, so I'll just tell you what are all the things will be covered as a part of our ATPG topic. So we will be covering we'll be understanding what is ATPG. Okay, we will understand what is ATPG. Okay, what is ATPG? Okay, and then we'll understand about the fault simulation. What is ATPG and what is fault simulation? We'll try to understand. So this fault simulation only, this fault simulation, that is what. So here we have written, right? So ATPG tool does fault simulation to generate the test pattern. So this fault simulation only, it is not a straightforward topic. Okay, so this itself might take around 2 sessions to understand completely. Okay, fault simulation itself might take around 2 sessions to understand because it is not a straightforward topic. Okay, and then we will be covering the various fault models. So we will cover the various fault models. Like these are all the fault models we will cover. So what is fault modeling? We will cover it. Okay, what is called as fault modeling? We will understand it when we do the course. And these are all the various fault models which we'll be covering. So one is the StuckCAD fault model. Other one will be the transition delay fault model. Then we have the path delay fault model. So this transition delay fault model and path delay fault model together we call it as the at-speed test. We will call it as the at-speed test. So transition delay fault model and path delay fault model, we will call it as at-speed test. And then we will be covering the IDDQ fault model. Okay, so these are what is fault modeling also we will understand. And we will also be covering all these fault models. So StuckCAD fault model, transition delay fault model, path delay fault model. So transition delay and path delay fault models, they are called as the at-speed test. And then IDDQ fault model. So these are all the fault models we will be covering. And then we will also be covering about fault dominance, and then fault equivalence. Okay, and then fault collapse. So we will be covering all these things. Fault dominance, fault equivalence, fault collapse. So we'll be covering all these things. And then we will cover the fault classes topic. So we'll cover the fault classes topic. So fault classes, So basically faults, they are broadly classified into two. One is testable class and the other one is untestable class. One is testable class and the other one is untestable class. Okay. So inside the untestable class, again you have the subclasses like unused, tied, blocked, redundant. Okay. And inside testable, you have these subclasses like detected, possibly detected, ATPG untestable, undetected. Again, these will be further classified. Like detected means it will further be classified as detected by simulation, detected by implication. ATPG untestable, it will further be classified as pin constraint, sequential depth, etc. So all those things about the various fault classes and their subclasses, all those things we will try to understand in the fault classes topic. Okay, and then we will try to understand about test point insertion. What is test point insertion? We will try to understand. We will try to understand about pattern classification, and then we'll understand about fault aliasing, and then we'll try to understand what is called as coverage, what is test coverage, what is fault coverage, all those things we'll try to understand. Okay, and then we'll try to understand about the on-chip clock controller, which is nothing but the OCC. Okay, the internal architecture of OCC we'll try to understand. Okay, and then we'll try to understand what is called as dead cycles. Okay, and we will try to understand what are the ways of detecting TDF faults, So that is nothing but LOC and LOS, and then LOS. Again, if you go for LOS technique, we need to add up a architecture called as pipelined scan enable. So what is that pipelined scan enable architecture? Okay, and then we will also try to understand when we have the timing exceptions. So timing exceptions. Okay, so what are the timing exceptions? Timing exceptions are nothing but the false path and multi-cycle path. So what is false path? What is multi-cycle path? We'll understand all those things. Okay, and how it is regarding this false path and multi-cycle path and all, how it is taken care in StuckCat. Okay, what will happen in the case of TDF? What will happen in TDF? Okay, like this we'll try to understand. We'll try to understand about the timing exceptions. Like timing exceptions are nothing but the false path and multi-cycle path. So what is this false path? What is this multi-cycle path? You'll be able to understand. Okay, and we will also understand if you have this false path and multi-cycle path, how it is taken care in StuckCat and what will happen in TDF. All those things we'll try to understand. Okay, so this was actually a very vast topic and it is also not a straightforward topic. So as I told, it will minimum take 10 and maximum 12 sessions to complete. Okay, each one is actually a vast topic. Okay, here in the list of topic here, I've just given the overview of it. Overview headings alone I have just written, but each topic it will take a long amount of time to complete. Okay, each topic. So say for example, you take this fault classes topic, so that will separately take one session to complete. This one it will take separately one session to complete. Like that, each one it will take a lot of time to complete. Okay, number of hours will be more to complete the topics. Okay, so this fault classes it can take around 2 sessions actually. Sorry, 2 sessions it will take to complete, like that. Okay, so each one is a very vast topic. And so that's why this complete ATPG, it's not a straightforward as well as it's a vast topic. So it will take around 10 to 12 sessions to complete. Okay. So yeah, now next is simulations. So simulations means it is actually to validate the patterns which was generated during ATPG. Okay, simulation means it is actually to validate the patterns which was generated during ATPG. Okay, so which means before delivering the patterns generated during ATPG, to test the chip after manufacturing, we need to validate once whether proper patterns are generated or not. So that is what is called as simulation. Okay, so before delivering the patterns generated during ATPG, to test the chip after manufacturing. To test the chip after manufacturing, okay, we need to validate once. Validate once whether proper patterns are generated or not. Whether proper patterns are generated or not. Okay, so before delivering the pattern generated during ATPG, to test the chip after manufacturing, we need to validate once whether proper patterns are generated or not. So that is what is called as simulation. So it is actually to validate the patterns which was generated during ATPG. So before delivering the patterns generated during ATPG, to test the chip after manufacturing, we need to validate once whether proper patterns are generated or not. So that is what is called as simulation. Okay, so why do we need to do this? So basically in the simulation topic, we will understand what happens in simulation. What is the simulation? Okay. And then what is the need of simulation? So what is the need of simulation? It is actually to validate the patterns which were generated during ATPG. So before delivering the patterns generated during ATPG to test the chip after manufacturing, we need to validate once whether proper patterns are generated or not. So that is what is called as simulation. Now, why do we need to do that first? Why do we need to do it? Why do we need to validate the patterns which was generated during ATPG? We will try to understand. We'll try to understand when we do the need of simulation topic. Okay, we'll try to understand when we do the need of simulation topic. Okay, and then flow of simulation. We'll try to understand what is the flow of simulation, and then we'll try to understand like serial and parallel simulation. What is serial simulation? What is parallel simulation? Okay, we'll try to understand these things. Okay, and how to analyze the waveform. Okay, so how to analyze the waveform, analyzing the waveform. Okay, and then like if in case you're like how to analyze the signals in waveform, all these things. And then if in case your simulation fails, how to do the debug. Okay, so simulation mismatch debug. So if in case your simulation fails, how you can do the debug. So that is what a simulation mismatch debug. We'll try to understand. Okay. So for simulations, we will cover both theory as well as practicals. We will cover it simultaneously. Done simultaneously. Okay, so all these things will be covering it in our simulation class. So these are the concepts which we'll be covering. So we will do the theory as well as practicals. We'll be doing it simultaneously. We'll be doing the theory and practicals simultaneously. Okay, we'll be explaining these concepts by practically demonstrating it in the labs. Okay, so theory and practicals, we'll be doing it simultaneously. Okay, and as I told, in simulations, only no timing simulation is covered as of now in our DFT course. Only no timing simulation is covered. Okay, currently in our DFT course, as of now in our DFT course, only no timing simulation is covered. Okay, and then next we will go to this JTAG. So JTAG, the full form of JTAG is Joint Test Action Group. Okay, the full form of JTAG is Joint Test Action Group. So it's a IEEE 1149.1 standard. Okay, it is a IEEE 1149.1 standard. Okay, so the full form of JTAG is Joint Test Action Group. So it's IEEE 1149.1 standard. Okay. So what is the need of JTAG? Why do we need to use JTAG? So one need of JTAG, it is actually to minimize the number of ports from top level, and the other need is actually to achieve boundary scan. Okay, need of JTAG is to minimize the number of ports from top level, and the other one is to achieve boundary scan. Okay. So we'll try to understand how with the help of JTAG you are able to minimize the number of ports from top level. Now let us understand. Okay. So here in this case, if you see, I've kept a list of some signals like memory bypass enable, EDT bypass enable, int mode, X mode, int testable, X testable. Like this, I have kept some signals. So these are just a list of some important signals. These are a list of some important signals. Okay. So there will be many more signals like these. There will be many more signals like this. Many more signals like this. Okay. So these are a list of some important signals. There will be many more signals like this. Okay. So now, if all these signals are to be controlled from the top level, okay, if all these signals are to be controlled from top level, okay, like this, you are allocating a top level port in order to control the memory bypass enable signal, one top level port to control the EDT bypass enable, one top level port for int mode, one top level port for intel testable, one for X mode, one for X testable, and so on. If I allocate a top level port in order to control each and every signal, and as I told, these are just a list of some important signals. There will be many more signals like these. Now, if all these signals are to be controlled from top level, which means if you allocate a top level port in order to control each and every signal, okay, then what will happen? If all these signals are to be controlled from top level, what will happen? Number of top level ports will increase drastically. Number of top level ports will increase drastically. Number of top level ports will increase drastically. Okay, if all these signals are to be controlled from top level, number of top level ports will increase drastically. Okay, so that is why we use JTAG. To internally control the static signals. Okay. So here I've kept a list of some signals. These are a list of some important signals. There will be many more signals like these. Now, if all these signals are to be controlled from the top level, that means you're allocating a top level port in order to control each and every signal. Then what will happen? The number of top level ports will increase drastically. So that's why we make use of JTAG to internally control those signals. Okay. So when we do the JTAG topic, you will be understanding what is the need of JTAG. Again, this need is there, and we'll try to understand it more in detail. Okay, as of now, just given an idea. When we do the course, we will understand more in detail about the need of JTAG. So we'll try to understand the need of JTAG. And here, if you see, I mentioned that we use JTAG to internally control static signals. So we'll understand what is called as a static signal and what is a dynamic signal. So difference between static and dynamic signals we'll try to understand. Difference between static and dynamic signals. Okay. And then we'll try to understand about the JTAG tap architecture. We'll try to understand about the JTAG tap architecture. Okay. And then we will understand about the JTAG controller. So JTAG controller is basically a 16-state FSM. JTAG controller is a 16-state FSM. So when we understand about this JTAG controller, the 16-state FSM, we will simultaneously explore how with the help of JTAG we are able to internally control the static signals. Okay, we will simultaneously explore. Okay, while we are understanding this JTAG controller is a 16-state FSM, while understanding the various states of this JTAG FSM, we will simultaneously explore how with the help of JTAG, we are able to internally control the static signals. We are able to internally control the static signals. Okay. And we will also be covering, as I told, we will also be covering the IEEE 1687 standard, which is nothing but IJTAG. So I've not included it in the demo because, like, in order to understand about this IJTAG, you first need to understand about JTAG, TAP architecture, all those things you need to understand. So that's why I have not included this IJTAG. What is IJTAG in the demo? I've been included, but in the regular course, we'll be covering IJTAG also. Okay. So what we will be covering is we will be understanding like the architecture. We'll be understanding about the architecture. And we will do a comparison between JTAG and IJTAG. We'll do a comparison between JTAG and IJTAG. Okay. And we will also understand about the advantages of IJTAG. We'll also understand about the advantages of IJTAG. Okay. So all these things we will be covering it in our course. Okay. And then boundary scan. Another need of JTAG is to achieve boundary scan. So what is boundary scan? We'll try to understand. Chip 1, chip 2, chip 3, they are properly passing the test of DFT, but still the board is failing. So what does this mean? Let's try to understand. So what will happen? First, chips will be manufactured. Chips will be manufactured. Okay. So first what will happen? Chips will be manufactured. And then what will happen? Chips will be tested on the AT. After this, chips will be tested on the AT. Chips will be tested on AT. AT is nothing but the tester. Chips will be tested on the AT, which is nothing but the tester. Okay, like this. This is the AT. The full form of AT is automatic test equipment. Okay, full form of AT is automatic test equipment. We also call it as the tester. Okay. So this is how this is nothing but chip 1. So input of the chip will be connected to the AT, output of the chip will be going back again to the AT. Same way, this is chip 2. Okay, and then this is chip 3. In this example, I've shown only 3 chips, right? Like this. So input of the chip will be connected to the AT and output will be going back again to the AT. Okay, so now here in this case, chip 1, chip 2, chip 3, they have passed their test on AT. They have passed their test on AT. Okay, chip 1, chip 2, chip 3, they have passed their test on AT. Passed their test on AT means, as I told in the earlier slide, output of chip, it is equal to expected output. Output of chip is equal to expected output, as I told in the initial slides. Okay, so chip 1, chip 2, chip 3, they have passed their test on AT, which means output of chip is equal to expected output. So which means that chip 1, chip 2, chip 3, they are not having any manufacturing defects. They are not having any manufacturing defects. Okay. So now after this, what will happen? The chips will be placed on the PCB board. Okay, so chips will be placed on PCB board. Okay, so like this is the board. This is the PCB board. Okay, so like this, the chip 1, chip 2, chip 3, they are placed. And then the interconnection between the chips and all are formed. Okay, now after this, what is happening? The board is being tested. The board is tested. Board is tested, and what is happening? It is failing. The board is tested, and what is happening? It is failing. Okay, the board is being tested. So what is happening? It is failing. Okay, why it is failing? Because chip 1, chip 2, chip 3, they are internally not having any manufacturing defects. They have already passed their test on 80. So chip 1, chip 2, chip 3, they are not having any manufacturing defects. Then why is the board failing? So this can be due to the manufacturing defects in the interconnection between the two chips. So this can be due to the manufacturing defects in the interconnection between two chips. Interconnection between two chips. Okay, so this can be due to the manufacturing defects in the interconnection between the two chips. So when the board is being tested, it is failing. Why it is failing? So chip 1, chip 2, chip 3, they are internally not having any manufacturing defects because they have already passed the test on 80. Now, why is the board failing? So this can be due to the manufacturing defects in the interconnection between the two chips. So in order to test the interconnection, between two chips, we go for boundary scan. Okay, we go for boundary scan in order to test the interconnection between two chips. Okay, we go for boundary scan to test the interconnection between two chips. Okay, so now in this boundary scan topic, what are all the things we will be covering? It is, so we will be covering the boundary scan cell structure. Okay, we'll be covering the boundary scan cell structure, and then we'll be covering the modes of operation of boundary scan cell. Okay, and we'll also be covering certain instructions like sample preload, X test, bypass, like that. We'll be covering some instructions. Okay, so sample preload. Okay, and then X test, and then bypass. So we'll be covering certain instructions. Okay, so when we do these instructions like this sample payload and X test, when we do these instructions, you will be able to understand like how with the help of JTAG. So here I've written, right, one need of JTAG is to achieve boundary scan. I've written here. So when we understand about this, when we understand about the boundary scan cell structure, the boundary scan chain, and then about the sample preload and X test instruction, all those things when we try to understand, you will simultaneously be able to understand how with the help of JTAG we are able to achieve boundary scan. Okay, when we do the course, you'll be able to understand how with the help of JTAG you are able to achieve boundary scan. Okay, and then next one is MBIST. So full form of MBIST is memory built-in self-test. So as its name suggests, we actually used MBIST technique in order to test the memories. Okay, so basically in this MBIST topic, what we will be covering is we'll be covering the basics of memories. Just for a short time, we will cover the basics of memories like RAM and ROM, and then types of RAM. So like that's a basic concept, basics of memories. Just a small, for 10 to 15 minutes, we'll just tell about the basics of memories. Okay, and then we will try to understand about the various memory fault models. We will try to understand. Okay, so the stuck at, transition fault, and then address decoder fault, coupling fault, like that. The various faults we'll try to understand: stuck at fault, transition fault, address decoder fault, coupling fault. These are all the various memory fault models. So we'll understand about that. And then memories, they will be tested using generalized algorithm. Okay, so memories, they are tested using generalized algorithm. Okay, so why or how memories are tested using generalized algorithm? How are we able to test the memories using generalized algorithm, or why we use generalized algorithm in order to test the memory? We will try to understand it when we do the course. Okay, when we do the course, you'll be able to understand why we make use of certain generalized algorithms in order to test the memories. Okay, so these are the various, some basic algorithms we will cover, like 0-1 algorithm. Okay, and then checkerboard algorithm. Okay, and then we'll be covering the MATS algorithm, MATS plus algorithm, MATS plus algorithm, MARCH algorithm. Okay, March C algorithm. Some basic algorithms we will cover. We will take some basic algorithms like this. And for each algorithm, it will be having a sequence. Each algorithm will be having a sequence. So we'll try to understand what is the sequence of each algorithm. And we will try to understand which algorithm will be able to cover which faults in memories and how. Okay, so which there are these are the memory faults, right? So which algorithm will be able to cover which faults in memories and how we will try to understand. Okay, which algorithm will be able to cover which faults in memories, which faults in memories and how we will try to understand. Okay, so which algorithm will be able to cover which faults in memories and how we are able to cover them, we'll try to understand. Okay, and then we will also cover about tessent MBIST. So tessent MBIST means if you are going to do MBIST using tessent tools. Okay, so implementing MBIST using tessent tools. So that is what is called as tessent MBIST. How you are going to implement how you are going to implement MBIST using tessent tools. Okay, so we will, that is what is called as tessent MBIST. Okay, so when you're using tessent tools, how the MBIST will be implemented. Okay, tessent is nothing but the mentor graphics tools. Okay, so when you're using mentor graphics tools, how the MBIST is implemented. Okay, or how the MBIST is done. So that is what is called as tessent MBIST. Okay, so in tessent MBIST, we will be covering the tessent MBIST implementation. Okay, we'll be covering the tessent MBIST implementation. Okay, we'll be covering the tessent MBIST implementation and architecture. Okay, we'll be covering the tessent MBIST implementation and architecture. So we will be covering the tessent MBIST operation protocol. Tessent MBIST operation protocol. Okay. So while understanding this, we will understand about these signals like the BIS setup signal, BIS setup, and then MBIST PG enable, MBIST PG enable, and then the go signal, done signal. So these are all the various signals. Okay, we'll try to understand about what are all these signals. When we do the tessent MBIST operation protocol, we'll try to understand about all these signals. Okay. And then we will understand the concept of grouping of memories, group concept. We'll understand about the step concept. Okay, the group and step concept, all those things we'll try to understand. Okay, and here, what is the full form of MBIST? Memory built-in self-test. So why it is called as self-test? Why it is called as built-in self-test? Okay, why is it called as built-in self-test? We'll try to understand. Okay, why is it called as built-in self-test? We will try to understand. Okay, so yeah, and when we do the course, you'll be able to understand why it is called as self-test. When we do this topic, you'll be able to understand. Okay. Okay, so now whatever overview I have given, it was from a theory class side. Okay, from a theory class side, I have given the overview. So next, let us discuss from the lab side. Okay, next, let us discuss from the lab side. So in our labs, what we will be covering is we'll be covering IJ tag insertion, MBIST insertion, scan insertion. So basically, there are two approaches in scan. One will be the top-down approach, and the other one will be the hierarchical approach. So we will cover both the approaches in scan. Okay, and then EDT OCC insertion, ATPG pattern generation, ATPG and MBIST simulation. So these are all the topics we will be covering it in our labs. Okay, so boundary scan we will be covering only theory. Boundary scan, we will be covering only theory. Okay, only theory will be covering it in boundary scan. So these are all the things we will be covering it in our labs. Okay. And now, basically our labs, it is actually divided into 4 levels. So level 1, level 2, level 3, level 4. Okay, it is actually divided into 4 levels. Okay. So the questions which is there in the chat box, like I will address it at the end. Okay, once I complete this PPT, I will just address the questions which is posted in the chat box. Okay. So basically, like our labs, they are actually divided into 4 levels. So level 1, level 2, level 3, and level 4. Okay. So basically, this level 1 and level 2 projects, they are simple test cases. They are simple labs. Simple labs. So which means their complexity will be less. Their complexity is less. So which means you'll be having maximum of around 100 to 200 flops will be there. Okay, maximum of around 100 to 200 flops will be there. 100 to 200 flops will be there. Okay, so this level 1 and level 2 projects, they are simple labs, so complexity will be less. So maximum of around 100 to 200 flops will be there. Okay, so totally you will be having 11 test cases. So in level 1 projects, you are totally having 11 test cases. So for these 11 test cases, we'll be performing the scan insertion. Okay, so among these 11 test cases, 2 test cases will actually be to familiarize with the flow. 2 test cases will be to familiarize with the flow. Okay, familiarize with the flow. Okay, 2 test cases will be to familiarize with the flow, and the remaining 9 test cases, you'll be having DRC violations. You'll be having DRC violations. We'll try to analyze the DRC violation in the schematic. Okay, and then like we will try to debug those DRC violations. We'll try to fix the DRC violation. And basically, while using Tessin tools, we'll be having 3 methods with which you can fix the DRC violation. So one will be the manual editing of netlist method. One is the manual editing of netlist method. Okay. And then other method will be to use this create instance, delete connection, create connection, those things. Some commands will be there, some Tessin tool commands with which you can fix the DRC, or else you can go for the auto fix method. Okay, so we will cover all these methods of fixing the DRC violation, and we'll also show, like, we'll also compare all these 3 methods, and we will tell you like which method is more preferred and why it is more preferred. Okay, so this is what. So total 11 test cases are there. 2 test cases will be to familiarize with the flow. Familiarize with the flow means, like, say for example, what is scan insertion? Scan insertion means normal flop will be converted to scan flops and scan chains will be stitched. Now, if you want to do this, with the help of Tessin tools, you'll be having a set of steps. You need to follow a set of steps. Okay, if you want to do this using Tessin tools, you need to follow a set of steps. That is what is called as flow. That is what is called as a flow. Okay, so you'll be having setup phase, analysis phase, insertion phase. So setup phase means you need to read the design and library file. You need to do the elaboration. You need to provide the declaration and constraint. In analysis mode, you need to check for the DRC violation. If there is DRC violation, go back to setup phase, fix it. If there are no DRC violation, go to insertion. In insertion phase, you need to replace all the normal flop with scan flops and do the scan chain stitching. And then you need to write out the reports and outputs. Like that, there is a set of steps will be there. Okay, steps will actually be there. Okay. You'll be having a, so if you want to do scan insertion using Tessin tools, you need to follow some steps. That is what is called as flow of scan insertion. So first two test cases which we'll be covering, it will be to familiarize yourself with that flow. Okay, what are the steps you need to follow for implementing scan insertion using Tessin tools? So you'll be able to understand that. These test cases will also be helpful to understand the various Tessin tool commands and then the Tessen tool environment, how the Tessen tool shell will look, how the Tessen shell will look, how the Tessen schematic will look, all those things. In order to familiarize with all those things, we'll be having 2 test cases. And the other 9 test cases, in all the other test cases, you will be having DRC violation. And we will be debugging the DRC violation. We'll be analyzing the DRC violation in the schematic and we'll try to debug them. Okay, and we'll try to fix them. So basically, there are 3 methods with which you can fix the DRC violation, like manual editing of netlist, or else you can have a create instance, delete connection, create connection. So these are a set of commands with which you can fix the DRC, or else you can go for the auto fix method. So all these 3 methods we will cover, and we will show like we'll do a comparison between all these 3 methods, and we'll try to understand which one is more preferred and why it is more preferred. Okay, and yeah, that's it. And we will also try to understand about the reports and outputs of scan insertion. The various reports and outputs of scan insertions are there, right? So that also we'll try to understand. Okay. So same way for the scan compression labs. For the scan compression is nothing but EDT insertion labs. We will understand the flow of EDT insertion, and we'll also try to view the logic in the schematic. Okay. And we'll also try to understand about the various output files generated. We will understand the various output files which is generated. Okay. And then for ATPG, we will be like working on these 3 fault models. So stuck at fault model, transition delay fault model, and IDDQ fault model. So we'll be generating patterns for these 3 fault models in our lab. So stuck at fault model, transition delay fault model, IDDQ fault model. So ATPG, here also we will understand about the flow, and we will work mainly on coverage analysis and improvement. Okay, we will work mainly on coverage analysis and improvement. Okay, we'll be working mainly on coverage analysis and coverage improvement. Okay, what is coverage analysis? What is coverage improvement? And how you can improve the coverage? So we will mainly be working on coverage analysis and improvement in our ATPG labs. Okay. And we will also here also we'll be generating patterns with TDT. With TDT also we will generate patterns, and we will also be generating bypass patterns. Okay, with TDT also we'll generate the patterns. We will also be generating the bypass patterns. So all those things we will cover it in our ATPG labs. Okay, and then simulation. Simulation here, whatever I have told so previously in the simulation topic, right? So 1 second. Here I had told, right? These are the things we'll be covering it in the simulation topic. So as I told, so simulation we will be like theory and practical, it will be done simultaneously. Okay, so these are the topics which we will be covering it during simulations. Okay. Okay, so simulation, whatever topic I mentioned earlier, so that is what will be covered. Okay, because the theory and practicals will be doing it simultaneously. Okay. And then next, coming to this level 3 and level 4 projects. So level 3 and level 4 projects, they are actually designs with higher complexities. Okay, these are the design with higher complexity. Okay, so these are the designs with higher complexity. So this will become the project work for your course. So this is what will become the project work for the course. Okay, so these are the designs with higher complexity. So they will become the project work for your course. So this level 3 and level 4 projects will be the project work of your course. You can mention it as a project work in your resume for this DFT course project work. You can mention this level 3 and level 4 projects as a project work in your resume. Okay. So basically, like in level 3 projects, you will be having around 4K flops. So around 4K flops will be there, and in level 4 projects, you'll be having around 44K flops. Okay. So level 3 projects. So in level 3 and level 4 projects, we cover the entire flow. So which means the IJ tag and MVist will be doing. ij tag and mbist insertion. Okay, then EDT OCC insertion. Okay, and then synthesis, then scan, ATPG, simulation, the complete flow will be doing. So if you just observe in our level 1 and level 2 projects, we didn't do this IJ tag and mbist, OCC insertion, all those things we didn't do it, right? Okay, but we'll be doing it completely, entirely we'll be doing it, all these things. The complete flow will be covered in the level 3 and level 4 projects. Okay, the IJ tag and mbist insertion, EDT OCC insertion, synthesis, scan, ATPG, simulation, everything will be covered in the level 3 and level 4 projects. Okay. And level 3 projects is hierarchical scan, level 4 projects is top-down approach. So level 3 projects is hierarchical scan, right? So we'll be covering some more concepts. So some more additional concepts also we'll be covering. Like we'll be covering about what is called as a scan wrapper. Okay, scan wrapper concept we will cover. And then we will understand what is in-test and X-test. In-test and X-test we will understand. And we'll also understand about pattern retargeting, what is pattern retargeting, all those things we'll try to understand. Okay, these are some of the extra concepts. When it comes to hierarchical scan, you need to understand about some more extra concepts. So that also we will cover. When we do the level 3 projects, when we do the hierarchical scan approach, we will simultaneously cover these theoretical concepts also. So scan wrappers, in-test, X-test, pattern retargeting, these are some more theoretical concepts which will be covered. So it will be covered during the hierarchical scan topic. Okay. So yeah. And then the tools which we'll be using it. So in our course, we'll be making use of the mentor graphics tools. So for mbist, we'll be making use of Tessent mbist. For scan, we'll be making use of Tessent scan. For scan compression, we'll be making use of Tessent test compress. ATPG pattern generation also will be making use of Tessent test compress. And simulation will be making use of QuestAsym. Okay. So at one stage alone, we need to run the synthesis. So that one will be making use of a synopsis tool, which is nothing but the design compiler. Okay, at one stage we'll be running the synthesis. So for that alone, we'll be making use of the synopsis tool, which is the design compiler. Okay, so yes. Okay, so these are the tools which will be used in our course. And then the other extra topics. So I will also, so these are the topics which is there in our course. And apart from that, some more extra topics like I will cover. So like in the previous batch, some of the students had requested for some topics. So I will be covering some more extra topics also. So I'll give an overview about those things. So in the previous batch students, they would have asked some topics, they would have requested some topics to cover. So I would have covered it for their batch. So for your batch also, I will give an overview about those topics. Okay. So previously, whatever I told, that is the part of our syllabus. So we'll be going in detail. So these extra topics, I will be giving you an overview about it. Okay, I'll be giving you an overview about these extra topics. So one is IEEE 1500 standard, and then about this RAM sequential, and then ROM mbist, and then K rules, F rules, so logic based, all these things I'll give you an overview. Okay, this is not a part of our syllabus, so I'll just give you an overview about these topics: IEEE 1500 standard, RAM sequential, ROM mbist, K rules and F rules, LBIST. So for all these things, I'll give you an overview. Okay, and apart from that, I will also be covering static timing analysis. So that also I will give you an overview. So STA is not the scope of DFT engineer, but some companies, they expect you to have an idea about STA, like what is static timing analysis, what is setup time, what is hold time, what is setup violation and hold violation, how you can fix the setup and hold time violations. Okay, some questions relate, so some problem questions related to setup and hold time. So they'll give you a circuit and they will ask whether setup or hold time is violated or not. Okay, and then setup or hold time is violated or not, and then what is the maximum frequency of operation. So such kind of some questions also they can ask. So whatever is asked in a DFT interview, okay, in a DFT interview, what kind of questions is asked in the interviews, okay, for STA topic. So such kind of questions I have collected, and I'll give you an overview about those things. So overview about STA, that is the models of questions which will be asked in a DFT interview. So those things we will give you the training. Okay. And yeah, okay. So basically, when you enroll into this course, so first what you'll have is you will be having the basic course. So first you will be having the basic course. Basic course will be there. So basic course, it will go for around 2 to 2.5 months. You'll be having the basic training. So for basic course, these topics will be covered. So GVIM, and then digital design, and then Linux, Pickle, CMOS, Verilog. So these things will be covered during our basic course. So first 2 to 2.5 months, you'll be having the basic training. So where we'll be covering all those things. So GVIM, digital design, Linux, Pickle, CMOS, Verilog. So all those things will be covering. Okay. After this, you'll be having the advanced course. DFT advanced course you'll be having. So DFT advanced course, it will be for around 3.5 months to 4 months. DFT advanced course will be for 3.5 months to 4 months. Okay, DFT advanced course will be around 3.5 months to 4 months. Okay, so what we will be covering, all the topics which we discussed in the previous slides, right? So that is what will be covered in this advanced course. Okay, so all the topics discussed in the previous slides. Will be covered. Okay, so all the topics which we discussed in the previous slide, so that is what will be covered in this advanced course. Okay, and then who can attend this course? So any student who is in the final semester seeking DFT as their course curriculum, you can attend it. So new college graduate who is from relevant branches of engineering and science. Lecturers or professors, if you want to switch your career into real-time industry experience, you can attend the course. And working professionals with similar or other VLSI domains. So say, for example, you're a physical design engineer. Now you want to shift your domain to DFT. You can attend this course. Or else you're in IT, and if you want to switch your career to VLSI, you can also attend this course. Okay. And then placement support. So placement support will be having tie-up with various VLSI companies. So student entitled to placement support based on the performance in their course assignment. So like during the course, we'll be giving you certain assignments, presentation sessions, mock interviews, and then tests. All those things we'll be conducting. So based on your performance, we will be adding you into a group called as the job support group. So in that job support group, they will be posting the placement opportunities. Okay. And then mock interviews will be conducted so that you can you can confidently attend the main interviews. So mock interviews will be conducted. Previous interview question preparations and answer. So previous batch students, while facing the interviews, they would have undergone some application oriented interview questions, right? So we will be discussing those questions along with the answers. We will be covering them so that you will be able to tackle similar kind of application oriented interview questions if it is asked in your interviews. Okay, so previous batch students, while attending the interviews, they would have faced some application oriented interview questions, right? So those things also we will provide the training so that you will also be able to tackle them. Okay, so yeah, that's it for my demo. And now let me just check the chat box and answer those questions. Elbest, so Sachin, like as I told, will be covering the overview. Okay, it's not a part of our syllabus. I'll be giving you an overview about Elbest. Okay. And Sudhakar, any reference book, I will be able to brush up my basics again. So basics anyways, it will be covered during this time. Okay, so the basics right from the beginning, the basics will be covered. So the digital design, these are all your basics. Digital design, Verilog, these are your basics. So these things will be covered again in the course itself, in your basic part of the training, right from the beginning, it will be covered. Okay, so all the topics will be covered. Whatever is required for understanding the advanced course, so all the basic topics will be covered. Okay, so there is directly you can attend the course. There's no need for you to brush up the topics. It will be covered in the course itself. Okay. Prepared for IAS after. Sudhakar, like I'll just share with you Vaibhav sir's number. Can you once check with sir? Sir will be able to guide you on that. Once again, I'll just share with you his number. So this is Vaibhav sir's number. Once again, let me just check if I've typed correctly. Okay. Yeah. So this is Vaibhav sir's number. You can just check with sir. Related to any queries, you can just contact sir. Like when is the course starting for your batch, whether it will be like online or offline, and then like what will be the schedule for your batch, and then regarding the placements. Okay, if you want to know something related to placements. Okay, and questions like these. So if you have a career gap, will you be getting placement opportunities? So all these kind of questions you can check with Vaibhav sir. Okay. Any other questions you have? Okay, then if there are no questions, then I think we can wind up with the session. So if you have any questions, as I told you, can contact Vaibhav sir. Number of vacancies compared to DV. Even that, can you please check with Vaibhav sir? So I'm not sure about it. So you can just check that with Vaibhav sir. Okay. So if you have any questions, you can contact uh, sir. Or else if an individual group is created, you can directly post your doubt in that group. So there will be a VLSI Guru ID and your name. One individual group would have been created. So when you enroll into the course, a group will be created. You can directly post your doubts in that group, or else you can contact Vaibhav sir. Okay. Yes, Chandu. Okay, I will. While taking the regular course, I will try to keep my pace little slow. Okay.
Ma'am, how to revisit this class, ma'am? I just want to see once again, like
Which platform?
this demo class, ma'am.
You want to see the demo class video?
Yes, ma'am. Yes.
Okay. Like is an individual group created for you with your VLSI Guru ID and your name?
Okay.
Is it created? So if it is
No,
created, you can just
no, ma'am.
not created.
Actually, I will enroll on Monday. From Monday onwards, my class will start. I just want to see this demo class again, ma'am. Whether it will be available.
Actually, like demo session, if you request to the institute, they will upload it in the YouTube and they will share with you the link. The regular class videos and all, it will be uploaded in the InSkill portal directly. You will be having an InSkill login, right? There, the regular classes will be directly added. For demo session alone, if you request it to the institute, they will upload it in YouTube and they will share with you the link.
Okay. Thank
You
you so much.
understood, right? Okay. You can
Yes, ma'am.
contact Vaibhav sir itself. He will inform or he will share with you the other contact who can provide you with the
Okay.
recording.
Okay, ma'am. Thank you.
Okay. So anything else you have, you can let me know.
Madam, tomorrow also do we have this demo class?
No, tomorrow you don't have demo class.
Okay, madam. From Monday the regular classes will be having.
Yes, correct. You'll be added up into a DFT group. So the session schedules will be posted in that group.
Okay, madam.
Okay. You can follow the schedule. Like you will be that particular week's schedule, they will be posting it into the group. I think tomorrow they will be sharing the schedule for next week's class. So as per the schedule, the classes will commence.
Okay. Thank you, madam.
What's your suggestion after completing each class, ma'am? What we need to do? Whether we need to take notes and revise that, or do some works, surfing on internet like that for particular words like ATPG and all to learn more about that.
Yeah, I will be uploading the session notes into the Google Drive. You can brush up those session notes, and if you just check in the internet, there will be very many various people. They will be writing some blogs or some articles. They will be writing. You can even read about their articles as well. The blogs and articles also you can just read it in order to. And some of them would have shared some interview questions, some things they would have shared. So if you just go through it, then you'll be able to you can deeper your understanding by reading those things. So if you
Okay,
want
ma'am.
to
So
do some
your
extraordinary,
suggestion is like classes, notes, and surfing on internet, and the work will be done for the interview. Interview ready preparation will be done, correct?
yes, correct. So usually
Okay, thank
surfing on internet, if you are interested, you can do it. Otherwise, it is not required. If you're
you. Okay, thank
interested
you.
to just deeper your understanding, you can read from some more sources. Otherwise, it is not very necessary to surf in the internet. Okay, if you want, you can
Yes,
just
ma'am.
read some blogs or articles.
Yes, ma'am. This whole course is based on that to crack the interview, and out what are the questions and
Yes, correct.
from the basics to the advanced level.
Yes,
Thank
yes,
you, ma'am.
correct.
Okay.
Only fresher syllabus or one or two experienced candidates. So mostly this course is designed for freshers, but even one or two experienced candidates have also in the previous batches, some few one or two experienced candidates, 1 or 2 years experienced candidates had also attended our course. So some 2 or 3 candidates in the previous batches, they had attended the course who had 1 or 2 years experience. But basically this course is designed for fresher. Okay, so in the previous batches, we had some 1 or 2 candidates who had some 1 or 2 years experience. But basically, this course is designed for a fresher.
BTech and ECI passed out in 2022. If I do this course, I'll be a trained fresher. Correct, ma'am?
Yes, correct.
Okay. So job opportunities are there, or I'll contact to Vibo, sir. Yes,
2022 is your pass out, right?
yes, ma'am. Yes, ma'am.
Yeah, you can once check that with Webhook, sir. So as far as I've
Yes.
seen, as far as I know, companies they don't specifically they are not mentioning the year of pass out. Most of the
They
companies
look
which I've
only
seen,
for their performance. Correct, ma'am. How I'm performing,
uh,
how I'm knowing the concepts and all.
yes, because in their requirement, in most of the companies, I have not seen year of pass out being mentioned. Only few companies they mention the year of pass out. But this is as far as I know. But Weber sir will be able to give a good idea on that because sir will be taking care of all these things. So you can just check that with sir. He will be able to guide you.
Thank you, ma'am. Intro about you, ma'am.
My name is Vidisha and I'm working with VLSI Guru for around 3.5 years. So I have around 18 batches of training, giving this training, DFT training. And I've also handled freshers I have also trained freshers from Juntron, and I have also trained the engineers from Intel Malaysia and Dell recently. So yeah, uh, that's it for my intro.
Okay. Thank you so much.
So
To perform well and good in this course, just follow the schedules and all the curriculums and the teachings. Correct?
yes,
Okay. Thank you so much.
okay. Okay. So thank you all. We will end today's class.